Welcome to this explainer. Today, we're going to untangle two foundational power system scheduling concepts that share a common goal, but actually solve very, very different problems. Let's be real here. A single modeling mistake in these calculations can cost a grid operator millions of dollars in a matter of hours. So if you've ever looked at grid optimization and wondered exactly where we draw the line between economic dispatch and unit commitment, you are definitely in the right place. We're going to break down the boundaries, the math, and the gritty physical realities of the grid.
We're going to build up our mental model today by layering on the complexity. We'll hit the two big questions, step inside economic dispatch, look at Lambda in real constraints, map out unit commitment across time, tackle the nested optimization problem, and finally, talk about choosing the right model. Starting right off with Section 1, the two big questions, identifying the decision space. To get our bearings, we have to start with the two deceptively simple questions that drive every single grid optimization model out there. So look at this split screen we've got here. Notice that persistent vertical divider right down the middle? We're going to keep these panels up on screen because this distinction is absolutely crucial. Over on the left panel, labeled commitment, we're looking at generator on and off status across time. It is binary. Are you on or are you off? Then, jumping across the divider to the right panel, labeled dispatch, we're looking at the actual megawatt allocation among those specific units that are already online. Knowing exactly which side of this line you're operating on is step one for any grid scheduling task.
Moving to Section 2, inside economic dispatch, distributing the load. Let's focus entirely on that right side of the screen for a minute.
In this economic dispatch model, that big on or off decision, it's already locked in. The commitment has been made. So now we're just playing with continuous variables, literally just allocating megawatts among the generators that are already spinning and available to move. We're not deciding whether to build a new factory or fire up a cold coal plant today. We're just telling the units that are already awake to push a little harder or back off a bit, all while keeping our total operating costs as low as humanly possible. To find that rock bottom minimum cost, we've got to look at the math. Every single unit has a total cost curve, which is just what it costs to produce at a certain output level. But the real magic? That happens with the incremental cost. That's the derivative, the slope of the curve, which tells us exactly what it costs to produce just one more unit of power. Assuming a perfectly lossless system with no active unit limits, the most economic solution balances the whole system by perfectly equalizing that incremental cost across all our interior units. It's actually a pretty beautiful concept. And we find that perfect balance using the classic Lambda iteration method. Think of it like a loop. First, we pick a trial value, our Lambda. We use that trial Lambda to estimate what each unit should output based on their specific incremental costs. Then we add all that hypothetical generation up and check it against the actual grid demand. Too low, we bump the trial Lambda up. Too high, we drop it down. We just keep iterating, looping round and round until the mismatch between power and demand falls right into our acceptable tolerance. It's super elegant, assuming perfectly unconstrained conditions.
Which brings us to Section 3, Lambda and real constraints. Mapping frictions. Because as we all know, a perfect, unconstrained grid doesn't actually exist outside of a textbook.
Here's where we really need to get our definitions straight. Lambda is a coordination quantity inside our mathematical model. Specifically, it is the shadow price of the power balance constraint. Now, if you were looking at an ideal, completely unconstrained, perfectly lossless, single price formulation, that shadow price might actually happen to coincide perfectly with the market clearing energy price. But you can't just blindly assume Lambda equals the real-world market price every time. Why not? Because real-world market prices are infinitely more complex. We've got all these systemic frictions that completely shatter that unconstrained ideal. I'm talking about transmission congestion. I'm talking about physical transmission losses as power travels over long distances. Then you have to factor in non-convex commitment effects, specific uplift charges, and all sorts of quirky market-specific settlement rules. All of these factors combined are what alter actual market prices and make them so much more complex than just a simple Lambda value.
And these frictions happen right down at the individual generator level, too. Imagine a generator slider hits a hard red maximum stop, or drops to a minimum operating floor. When that happens, the active set changes. That unit is now pegged. It's no longer an interior unit, which means our nice, elegant, equal incremental cost rule doesn't apply to it anymore. The leftover demand has to be shifted around to the units that are still free to move. Honestly, applying the unconstrained rule to a pegged unit is one of the most common engineering traps out there.
We also need to draw some hard lines around what economic dispatch actually is and what it isn't. It is definitely not automatic generation control, or AGC, which is a closed-loop system dealing with real-time frequency control. And it is certainly not optimal power flow, or OPF, which throws in highly complex network variables and limits like line flows and voltage conditions. Sure, they might interact, but they are absolutely not synonyms.
All right, section 4, unit commitment across time, the macro view. Let's zoom way out and look at the left side of our decision space again. Unit commitment is entirely intertemporal, meaning it's all about tracking decisions across time. Think about it. A choice you make at hour 1, like eating a massive startup cost to turn a plant on, creates strict path dependence. You can't just flick a giant power plant on and off like a bathroom switch. If it starts up, it usually has a minimum uptime. Let's say it has to stay on until hour 4. Then, if you shut it down at hour 5, you're hit with shutdown costs, and it might be forced to stay off for a minimum downtime until hour 8. These physical realities chain our hours together and severely limit what's physically possible later in the day. Moving into section 5, the nested optimization problem, bridging math and reality. Once we start tracking time, path dependence, and physical constraints across multiple hours, the mathematical complexity just skyrockets. Just look at the core mathematical difference here in this table. For economic dispatch, we're using continuous variables. Picture them as smooth, sliding megawatt dials. But for unit commitment, we're dealing with binary variables, hard, rigid on or off switches. The catch is that in the real world, we have to solve them simultaneously, and combining those smooth, continuous sliders with those binary switches plunges us straight into a highly demanding mixed integer reality. Which leads to this really profound takeaway. Economic dispatch is completely nested entirely within unit commitment. Every single time the model tests out a candidate on or off commitment schedule across the day, it still has to run the embedded continuous dispatch logic just to verify if those online units can feasibly and economically meet the load. That is exactly why these two concepts share the exact same objective of minimizing cost, but demand totally different mathematical models. Unit commitment is the overarching framework. Economic dispatch is the engine running inside it. Finally, section 6, choosing the right model, practical application. Why does mapping out all these boundaries actually matter for you on the job? Because being a truly great engineer isn't just about memorizing textbook equations. It's about having the judgment to pick the absolute smallest, simplest model that still gets the job done. If your online set of generators is totally fixed, economic dispatch is completely sufficient. Don't overcomplicate it. But if you're choosing unit status across time, you absolutely need unit commitment. Network limits mattering to your load better add optimal power flow, and if transmission losses matter, you have to explicitly include a loss-aware coordination condition, like a penalty factor. Do not add a feature unless you are answering a specific, declared need. This logical framework is the exact engine behind the Moonbow Readiness Kit's evidence loop you see right here. It forces you way past just being casually familiar with a concept. It pushes you to diagnose, learn, challenge your own assumptions, debug flawed formulations, and ultimately actively defend your chosen model boundaries out loud when the pressure's on. You need to know exactly why you picked the model you did. So, as you gear up for your next power system scheduling task, I want to leave you with this one critical question. Are you actually solving the real-world problem, or are you just trying to make the math look sophisticated? Choose your models wisely, because out there in the real world, the grid doesn't care about your elegant equations. It only cares that the lights stay on. Thanks for joining me for this explainer, and keep challenging those assumptions.